There are three isotopes of carbon we may find in nature. The most common one is carbon-12, which is stable and accounts for about 99% of all carbon. About 1% of the carbon we find in nature is carbon-13, which is also stable. And about 1 in every 1 trillion carbon atoms we find in nature is carbon-14, which is radioactive with a half-life of 5,730 years. Carbon-14 is formed in the upper atmosphere when cosmic particles hit nitrogen nuclei. As a neutron hits a nitrogen nucleus, the nucleus may transmute into a carbon nucleus under the emission of a proton. As mentioned, carbon-14 itself is radioactive, and it will eventually spontaneously decay into nitrogen-14 under the emission of an electron. The rate of formation of carbon-14 is approximately equal to its rate of decay, and the ratio of carbon-14 to carbon-12 in the atmosphere is stable at about 1.3 times 10 to the minus 12. Carbon-14 acts chemically the same as carbon-12 and will as such be incorporated in molecules such as methane and carbon dioxide. Since carbon dioxide is taken up by plants, which are in turn eaten by animals, the ratio of carbon-14 to carbon-12 in all living things is also about 1.3 times 10 to the minus 12. So when we run around or turn trees into paper or cotton into clothes, the ratio of carbon-14 to carbon-12 in our bones and sheets of paper and shirts is also about 1.3 times 10 to the minus 12. However, dead animals, sheets of paper, and pieces of clothing no longer exchange carbon with the environment. The carbon-14 is no longer replenished, and after one half-life, or 5,730 years later, the ratio of carbon-14 to carbon-12 has dropped by a factor of 2. This then allows us to determine the age of organic materials we find, as long as they are not too old. By counting the amount of carbon-14 and carbon-12 and comparing it to the ratio of carbon-14 to carbon-12 in the atmosphere, we can find out how many half-lives ago it was buried. Since the half-life of carbon-14 is of the order of a few thousand years, this method works particularly well for materials that were buried up to several tens of thousands of years ago. For much older materials, we can use other radioactive nuclides, such as lead-205, which has a half-life of 17 million years, or potassium-40, which has a half-life of more than a billion years. One extra challenge, in particular for such long half-lives, is that we may not always know what the original abundance of the various nuclides was. However, by using models and comparing the numbers we get from different radioactive nuclides, we can often get pretty good results.